My name is Vicky Rosengarten. I'm an advisory teacher for learning difficulties at Send Success, which is the Waltham Forest Send outreach service. And in this webcast, I'll be covering supporting dyscalculia and maths learning difficulties. The training will cover the following learning objectives. To understand the characteristics of dyscalculia and maths learning difficulty, and to look at some of the signs and indicators you might see in the classroom. And then to look at a range of teaching strategies to support the learners that display these features. And then finally looking at the processes involved in identifying and diagnosing dyscalculia. Characteristics of dyscalculia. Dyscalculia is a specific learning difficulty. It comes under the same umbrella as dyslexia, so meaning that an individual with a diagnosis will usually be cognitively able in all other areas and only have problems with their learning in mathematics. In relation to dyslexia, it's thought that research into dyscalculia is about 10 years behind where dyslexia is. There's much less known about the condition, but it is a growing speciality. This lack of research may be due to the fact that maths is not needed across the curriculum like literacy is. So there just hasn't been the same impetus. But there are some really important findings on how it can impact learning in school, and not just in relation to maths, which I'll share with you today. 4 to 6% of children are affected, and it's thought it's about the same prevalence amongst boys and girls. 25% of children have a maths learning difficulty, and dyscalculia would sit at the extreme end of the spectrum. It's a congenital condition, meaning that the child is born with it. It's caused by structural differences in the areas of a learner's brain responsible for numerical calculation. And comorbidity. It is a specific learning difficulty. However, possibly related coexisting conditions that can be commonly associated with dyscalculia are ADHD and autism, but it can prove difficult to untangle. 50% of dyscalculics also have reading issues. 4% are severely dyslexic. 40% of people with dyslexia have a significant difficulty with maths. However, 25% of dyslexics are above average in maths. There's some debate about the link between dyscalculia and dyslexia, and current thinking is that they're separate, so more research is needed. Number blindness, or a lack of number sense, is often used to describe dyscalculia. It's a difficulty with understanding simple mathematical problems that can also play out in daily life. Dyscalculia is not something we can cure, but there are strategies that can be learned to overcome some of the difficulties. So now I'm going to run a little test on you. Something similar would be used in the screening process for dyscalculia. You're going to see spots on the screen, and all you need to do is say to yourself how many you can see as quickly as possible. So how did you get on? With the smaller quantities, were you able to say how many there were without counting the spots one by one? With the previous slide, could you say how many there were without counting? And for this set of dots here, there are perhaps too many to know instinctively how many there are, so you can't say quickly. Most people, in fact, are able to recognise a quantity of up to 5 or 6 objects without counting. But I'm imagining you counted them either individually or perhaps you grouped them into twos or threes for speed and counted up that way, as you know that numbers are grouped in a system of related facts. Or maybe you used another strategy of counting one side as 5 and the other side as 5, and then you added them together. So what you're doing without too much thought very quickly is looking for patterns and then drawing on your previous mathematical knowledge of number facts about 5 or 2 or 3 to get to your answer. The ability to know how many dots there are in a randomly organised pattern without counting is called subitizing or dot enumeration, sometimes also referred to as numerosity. Subitize in Latin means sudden, so the quick recognition of a quantity. Someone with dyscalculia finds subitizing very challenging. They'd find it really difficult to be able to see that there are patterns within the dots and that these patterns relate to each other. And these relationships build up into regular networks and systems that can be built up but also broken down. When you quickly identified how many dots there were, you knew that a set of 2s builds into 10 when there were 5 of them, but also that a set of 3 3s plus 1 also makes the same quantity. This ability is known as number sense. We'll have a look at more detail at this as we move along. So this sense of number is innate. We're born with this ability to assess quantity. Babies as young as 3 months have been shown to be more attracted visually to larger quantities. This ability is a survival instinct. When we were hunter-gatherers, we needed to be able to estimate whether we were under threat by determining the magnitude of a group of animals, for instance. So a large group was a threat, but a small group could be a meal. This ability to recognise large or small quantities isn't unique to humans. It's been seen in chimps, chicks, salamanders and honeybees. But people with dyscalculia may not have this innate sense. This ability to assess large and small quantities is lacking. They may not even be able to subitize 2 objects. You might well be thinking, well, how could I help someone develop number sense? We'll look at this in greater detail below, but this slide begins to show you how by teaching children to see numbers organised into familiar, regular docked patterns, they're able to develop visual images of numbers as a whole, rather than a 10 being made up of 10 individual ones. These images are really important because counting up in ones is very limiting when you have to start to deal with larger numbers. You can't count out ones when you're having to deal with handing cash over in a shop or work out how long's left on a timer, never mind all the formal calculations required at school. Here's another little test used to determine whether the child's problems with number are due to dyscalculia or to other cognitive deficits. When shown this first picture and asked which is taller, people with dyscalculia answer this question just as quickly and accurately as people without a learning disability. However, when asked which is greater out of 2 numbers of the same physical size, dyscalculics take longer and are much less accurate answering this question. They have even more trouble when the difference between the 2 numbers is small like this, and this is known as the numerical Stroop test. So the ability to identify the digit symbol that represents bigger numerical quantity, regardless of size, is a challenge if you have dyscalculia. Brian Butterworth, a professor in cognitive neuropsychology, looked at the relationship between numerical values and physical sizes and found that people with dyscalculia have significant deficit in their ability to link a numeral with its meaning. For this last test, I'll ask you to put a mark on this number line where you think 64 would go. Now, I've already given you some information, such as where the 50 would sit on the line, which helps you to predict the next 50, so where 100 might go. So you can estimate the space that represents a decade from that, and then perhaps break that down further into 5s and then 2s until you felt confident where 64 would go. For someone with dyscalculia, visualizing the sequence of numbers building cumulatively along a line like this in a chronological order is really very hard and far too abstract due to poor visual spatial skills. They find it really hard to understand how number can be represented like this without an underlying grasp of the fact that numbers increase in quantity as you progress along the line. They may mark the 64 in any random place in the hope that it would be correct, but they have no underlying grasp of what the line represents. So I hope these 3 tests have illustrated some of the fundamental areas that dyscalculia and maths learning difficulties can cause problems with. So looking at the definition of dyscalculia now, there's actually no single widely accepted specific definition of dyscalculia, but a number of definitions that exist. This one in particular, I thought, summarises what we're looking at today. Dyscalculia is a specific and persistent difficulty in understanding numbers. Dyscalculia falls at one end of the spectrum and will be distinguishable from other maths issues due to the severity of difficulties with number sense, like we saw with subitizing, including subitizing, symbolic and non-symbolic magnitude comparison, so the difficulty understanding that a numeral represents a quantity, not being able to compare them, and ordering, so this sequencing on the number line. It can occur singly, but often co-occurs with other specific learning difficulties, mathematics anxiety, and medical conditions. So what's it like to live with dyscalculia? We're going to have a look now at how these issues might present themselves in the classroom, across ages from early years to secondary, by having a look at some case studies, starting with a little girl called Iris in reception. As I'm going through the list of difficulties, please remember the individual issues that Iris presents with here will not in themselves necessarily indicate that she has dyscalculia. They could indicate a whole host of other concerns, but what I wanted to illustrate were the kind of issues that may emerge that would be worth investigating further when they arise in combination. It's worth noting here that dyscalculia becomes more obvious as children get older and tackle more complex maths, but it can appear as early as 3 or 4. So Iris has trouble sorting things. She finds it hard to group items that share the same qualities like colour, shape or size. She's often asking, how much longer? So the sequence of time for Iris is hard to grasp. So she might ask about when lunchtime is, when she hasn't been in school for very long. She has trouble recognising number symbols and can't connect the number to the group of things. So you might ask her to match a digit to a group and she finds that really hard, and struggles to recognise patterns such as smallest to largest or tallest to shortest, so ordering by size is hard for her. And trouble learning to count and often will skip over numbers. It's really hard to memorise this sequence for some children, long after other children the same age can remember the numbers in the right order. It's worth noting that some children do memorise this order, parrot fashion, and that can mask underlying issues with this lack of understanding about what they're really saying. It could be just a string of words that always go together, much like a rhyme. So these are some of the signs that you may recognise in a child of 4 or 5. So let's have a look at an older child now. Mo is in year 4 and we're going to look at what he struggles with, which could indicate he has dyscalculia. In sports games, he struggles to keep score. It's reliant upon him holding numbers in his head, so his working memory is under strain and he finds that really hard. He struggles to understand words related to maths like greater than or less than. The language around maths can be really hard. He uses his fingers to count instead of more advanced strategies, particularly in mental maths, and struggles to identify math symbols and other signs and how to use them correctly, knowing that that shape represents a process or a system that needs to be applied. It's really abstract. So he gets lost during calculations as what he's supposed to be doing, and so might get muddled up and confused. This also relates to a difficulty with using numerals in place value systems and where to put them, which column to put them. Finds that really difficult. And he finds it hard to measure things like ingredients in a simple recipe. He doesn't have a mental image of the difference between 5 grams or 500 grams. So there's a problem with quantity, and fractions. Describing half of something is too abstract. So he just finds it difficult to estimate and will often write answers to calculations that are completely unreasonable and can't be possible. Has difficulty learning and recalling basic maths facts. And using a number line is a challenge, relating to an impairment in visual spatial understanding. So here we have James in year 9 now. He has a hard time grasping information shown on graphs or charts, so it's interpreting the data and extracting what he needs. He finds that really difficult to understand due to his visual spatial difficulties. And trouble working out how much money he needs in the canteen can be embarrassing. And difficulty measuring things like liquids in a bottle in a chemistry experiment. And trouble finding different approaches to the same maths problem. It relates to his impaired ability to generalize and transfer skills confidently. So for example, with a 2-digit addition sum, knowing that he could use a number line or the column method or partitioning. And in PE, when he runs a race, he doesn't pace himself and runs really fast for the first lap and then runs out of steam. And finally, we have a young lady who has a diagnosis of dyscalculia and describing what it's like to live with it and how it affects her daily living. If we start at the top here, she talks about bumping her head on everything. This seems unexpected for someone who lives with a math difficulty, but it would in fact relate to her difficulty with visual spatial abilities. And moving here to the right, she often arrives way too early. She has difficulties with the sequencing of time, so she manages that by overcompensating. And moving down here, working out the change when shopping is nerve-wracking. This can be really debilitating for people with dyscalculia and can have serious consequences. Rather than deal with the embarrassment in shops of not knowing how much money to hand over when shopping, they would prefer to shoplift, with obvious repercussions. Related to shopping here, she rarely knows what the sale price of an item is, as working out a percentage discount can be really hard. And here, directions like north and south don't click for me. And scheduling takes all her focus. So when she's planning ahead in her diary, difficulty with sequencing abstract ideas is really challenging. So you can see how having this impairment to mathematical ability can negatively impact a person's life significantly. Here we have a summary of the main challenges facing somebody with dyscalculia and maths learning difficulties. I've given you an overview of the common indicators, but I just want to draw your attention to the highlighted grey areas. Core number, reasoning, visual spatial, and memory, as these are the subtypes of dyscalculia, and dyscalculic learners may have difficulty in all of these areas, or maybe just one or two, which leads to a variety of maths profiles. Steve Chin, who is an expert in the field, has been dealing with children with dyscalculia for many years and understands how important it is to make sure that the children are taught according to their primary need. He argues that traditional teaching methods discriminate against dyscalculics. Through his work with 10 and 11-year-old students, who were 3 or 4 years behind where they should be, he matched teaching methods to the specific profile of the learner and raised the national pass rate of these pupils with maths learning difficulties from 50% to nearly 80%. Please have a look at his book called More Trouble with Maths for more details, which I've referenced at the end. And here we have a summary of the key indicators that are important to be aware of. This inability to subitize, so not being able to determine the number of objects in a small collection. Poor number sense. Dyscalculic learners just don't have a feel for number. At the most basic level, they don't know the threeness of 3. And just to reiterate, performing simple addition and subtraction is hard, so much slower to perform these calculations. And the chronology of the number system is also really difficult. Knowing where numbers should go, navigating forwards and backwards is challenging. And a poor memory for facts and procedures, and that numbers stand for a quantity. This inability to notice patterns, difficulty sequencing, and an inability to generalize. An inability to estimate. They have no sense whether an answer obtained is right or nearly right, or whether something is reasonable. This impaired sense of number size and trouble with quantity. And persistence in using immature strategies, which I want to have a look at in a little bit more detail now. To demonstrate the progression from immature to more advanced approaches, have a look at this simple calculation and reflect briefly on what you do to find the answer. For the students who persist in using immature strategies, being faced with this sum would potentially involve them counting from 1 to find the answer. Now this may be using their fingers, in which case, as we are bridging through 10, they would run out. Try to imagine what it might be like to be a child with dyscalculia who sees every number simply as a string of ones, one after the other. What happens is that even relatively small numbers and quantities lose their individuality. A string of single units hides any identifying characteristics, such as whether the number is odd or even, or how it can be built out of smaller components. If 8 is seen only as 1 plus 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 1, and 9 as 1 plus 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 1, neither quantity can be established except by counting, and either number is easily mistaken for the other. Gray and Toole carried out some research into which strategies learners used, and counting all with students below average ability in maths was the most commonly used approach. The next stage that children develop skills with is to count on. It's more efficient, but relies on this ability to hold a number in your head. Some children might count on from the left to the right in this instance, starting with a smaller number. We know that to count on from the bigger number is the more advanced approach, and the student demonstrates a grasp of magnitude. Using known key facts is next in developing fluency. The children are able to generalise their understanding of number. So they might just know that 3 and 4 make 7. It's one of their key facts. And the extra 10 in there means we add 7 to the 10 to get to 17. This automatic retrieval of basic maths facts is critical to solving complex problems, because complex problems have simpler problems embedded in them. So, for example, a long division problem has simpler subtraction sums within them. Students who automatically retrieve the answers to a simple subtraction can free up their working memory to focus on the long division. The higher attaining maths learners can make links, transfer key concepts, and draw on previous knowledge by using a derived fact approach. So in this instance, the student may know that 5 and 3 make 8 and 10 make 18. So 4 and 3 and 10 will make 1 less. Unsurprisingly, Gray and Toole did not find any low maths attainers using this strategy. I think it's worth having an understanding of how limiting it can be to be stuck at the counting all stage, and illustrates why some children take such a great deal of time to answer, especially when compounded with impaired working memory. You can see why a wrong answer can often be arrived at. In order to be able to derive facts, the children need to be taught strategies, and only once they have a secure bank of key facts. This is a summary of the stages taught in progressive order to Year 1 pupils, all facts within 10. So starting with adding 1, then doubles and near doubles of numbers to 5, then adding 2, numbers bonds to 10, adding 0 to a number, adding 10 to a number, and then the ones without a family. So these pairs of facts are the only ones which don't fit in any of the other families, though the last two can be related to counting in threes here. To secure fluency in addition and subtraction facts, taking a rote memorization approach is far less effective than teaching strategies. What's become important in maths teaching is for children to be able to do this without counting. They should be able to count fluently in odd numbers. By Year 2, the bridging 10 facts are being taught. So doubles of numbers to 10, near doubles, bridging. Before the children are ready to learn bridging as a strategy, they need to be able to partition all single-digit numbers. So adding 5 and 8, for example, you're bridging through 10, and it requires the children to partition 5 into 2 and then 3. Compensating. When a number can be rounded to the nearest 10 easily, add or subtract the nearest 10 and then take away or add back what you previously compensated. Once children have been taught the strategies, they need to move on to practice these facts. But just looking at this progression from the perspective of a child with some or all of the issues highlighted so far of having a maths learning difficulty, it's no wonder that maths anxiety can set in early. So dyscalculia is not another name for maths anxiety. Anxiety associated with maths can exacerbate problems with mathematical understanding, and it can lead to withdrawal from maths and a complete and total fear of anything related, to the extent that it can be really debilitating. The interaction of having anxiety on working memory is really significant, because anxiety reduces working memory. The more anxious somebody is about maths and a particular calculation, the working memory can become overloaded and then negatively impact on that person's ability to perform a calculation. They're just unable to retrieve the key facts they need. So they definitely go hand in hand, but anxiety needs to be taken really seriously, as children can develop very low self-esteem, which acts as a barrier to learning not only in maths but across all subjects. It's almost like a self-fulfilling prophecy of failure. Unfortunately, maths anxiety may be unwittingly caused by the teaching techniques that are sometimes used in maths lessons. Judy Hornigold writes about this, whereby it seems that more than in any other subject, there's this emphasis on timed activities and speedy answering. There's less time to really explore the processes involved. It's not so expected in other lessons in the same way, but in maths there's this expectation of rapid response, rapid recall, particularly in mental maths. It's a really heavy burden on the working memory. There's often competition encouraged amongst students as well, and lots of working in isolation, plus a focus on memorization of facts, like times tables facts, rather than really giving time to understand the meaning behind what the children are working through. We can't get away from the fact that maths is tricky. It's so abstract, based on concrete quantities and concrete relationships, and moving from a really early age, really swiftly, to abstract and symbolic representations. Some children have an intrinsic number sense and visual spatial competence and can handle this. However, without these innate skills, things move too quickly on. Arriving in nursery when things may already be beginning to move away from concrete into abstract, with an emphasis on learning math symbols, for instance, it can begin to put some children behind because they may have a weak symbolic understanding of number. And maths is a building block subject, so before they know it, they're lost. The more advanced layers of mathematics depend on the earlier understanding being secure. And the speediness to perform in maths is pushed, and finally problem solving relies on having a really good working memory to be able to hold on to the question, decide which strategy is being asked for and then the best course of action, keep the question in mind while following the necessary steps. The image here on the right is taken from a book written by Paul Moorcroft, who has dyscalculia, and it's called It Just Doesn't Add Up, which I've listed at the end. We're beginning to see how difficult it can be for a child with maths learning difficulties and dyscalculia, and how quickly any deficit in understanding can progress into becoming a significant problem. Further difficulties are compounded when we then look at all the inconsistencies found in maths. We're going to look at those now, starting with fractions. They're often viewed as really problematic by many learners. If I just illustrate this with one example here, when we add fractions, we only add the top numbers or the numerators together and not the denominators, yet when we multiply them, both the numerator and the denominator are multiplied. And moving to time, the language used in time can cause so much confusion. It's a meaningless, abstract concept made much more difficult to grasp if you have short-term memory difficulties and no intuitive understanding of number sequences. With regard to hours and minutes, a dyscalculic learner doesn't have a feel for what these are like in real life. We might use terminology like wait a minute when we don't actually mean waiting a minute. When we talk about seconds, it has so many different meanings in the English language. It could be second hand, which is actually the third hand and the fastest moving hand on a clock. So it's not the second fastest moving hand on the clock. The question of what o'clock also presents itself. When we talk about the day, the question of the day, is that daylight, the day as a whole is 24 hours, or the school day? The hands and face of a clock aren't like our hands and face. The language we use when reading a digital clock is different to that of an analog clock. So we may say 6:30 when we're looking at an analog clock, but then it's 6:30 when reading a digital clock. This can also be confusing when we see 7:10 on a digital clock, but say 7:10. When telling the time on an analog clock, we work clockwise. We count on from 1 hour, and then when we reach past, we count to the next hour. So 4:30 is 4:30, but 10 to 7 has neither a 10 nor a 7. It's 6:50 on a digital clock. When we say 1:45, a dyscalculic learner may not understand 2 is 2 rather than the number 2. We taught most maths using a straight number line, which is either vertical or horizontal, but in time the number line is circular. The 5 can be 5 o'clock or 25 past. There's no 0 at the beginning of a clock number line. And base 12 is used. So 60 seconds in an hour, 12 hours in half a day, 24 in a whole day, rather than base 10, which is used for everything else in maths. It's a minefield. The maths of time is just so abstract, and for some learners it's like translating time from a different language. It's a wonder that anybody has learnt to tell the time. I've got some more inconsistencies here. So we talk about carrying in addition sums and decomposing in subtraction sums. What other meanings do these words have for children? And to estimate, we expect absolute accuracy in answers at all other times, and then expect the students to abandon this when we ask them to estimate an answer. Decimals. We write whole numbers as getting bigger from left to right, units, tens, hundreds, thousands, and then in decimals, the numerals from left to right of the decimal point actually get progressively smaller. The hundreds and hundredths sound very similar but mean very different things. In subtraction, in early experiences of subtraction, we say the small number is subtracted from the big, such as 3 taken from 7. However, this doesn't remain a reliable concept when we start to deal with larger numbers. Thinking about the word minus on a temperature scale means less than 0. And multiplication may be taught as a process that makes things bigger. So just when the learner thinks they have everything under control, multiplying by half makes things smaller. And language. Often the teen numbers get confused with the decade. So 17 and 70, 16 and 60, for example. If you don't have a secure place value knowledge, mistakes can be made. And weight, when we're measuring, sounds like weight to weight. A table holds data in maths, but we sit at tables. And there are other words that have different words for the same concept. So to add, we might say plus or greater than, more than, and take away, subtract, less than, different, difference, or fewer. I hope I've raised some awareness of the incredibly paradoxical nature of the language around maths and the challenges it can present for any child, never mind someone with a learning difficulty in this area. We're now going to have a look at how to support a child who may have been diagnosed with dyscalculia, who you're supporting, or for a student who presents with the difficulties consistent with this profile. The strategies that I'll cover will be related to developing number sense, working memory, sequencing, the language of maths, and addressing maths anxiety. So let's start with top tips for developing number sense. We need to make the concrete out of abstract concepts before we can move on to pictorial representations. So use concrete manipulatives. They function as cognitive tools to connect students to concepts. They may make difficult ideas more understandable, complex problems solvable, and abstract concepts tangible. We're going to have a look at some of those below. So spend time exploring them and don't take them away too soon. They really will help to develop the child's understanding. Play with dice and dominoes to improve the recognition of spot patterns. When we looked at subitizing, we saw how helpful it was to position those 10 dots into a regular recognizable pattern to make them more memorable without having to count each dot individually. So play lots of games with these, as it helps the children develop visual mental models. Beware the counting trap. So this refers to counting in ones instead of looking at chunking numbers. Obviously we can't move on to this before the child is confident, and we don't want to demonise counting on fingers. But be conscious of your aim to move away from this because it's so limiting, and encourage the child to use counting on rather than counting all. Professor Eddie Gray showed that children who do not have a large store of number facts, of which they tend to fall back on, use habitual but laborious counting methods, a process that takes so much time and effort that the facts don't make their way into the learner's long-term memory, which means that their store of known facts remains as limited as ever. Gray's conclusion is that children need to learn how to compress the counting process and progress to more sophisticated, more efficient methods. And basically, children need to learn to see numbers as built not out of ones, but out of chunks or components, as Ronit Bird refers to them. So focus on games and activities and fewer worksheets. The games are really helpful as they're anxiety reducing, and so don't rush into abstract or written work. Encourage the child to visualise maths, draw diagrams and use the concrete materials to model maths. Give them multiplication grids and the number bonds to reduce the stress on having to remember these facts. Highlight the repeating decimal structure of the number system, meaning that the number system is made up of decades that repeat themselves. And once they're able to grasp that, it's really helpful. They'll be able to see the regularity of the pattern and take a step-by-step approach. Have a little and often approach with repetition and overlearning. So if you're finding a child is struggling in an area such as subtraction, reverse and take time to really overlearn the key addition facts so they can see the relationship between the different components of number. Again, lots of games around this, and I have references at the end to some really excellent resources. Multisensory teaching is really effective. Hands-on, switches, brains on. Some examples here. So visualizing here on the left. It's a great way to have the children represent maths operations. You can move the items around, they can see how the quantities change, a concrete way of understanding how the operations work. And then building gives them a concrete idea of measurement and the properties of the figures that they create. Or drawing maths problems. Maybe after working with hands-on materials, draw the maths problem could be the next step, and one step closer to writing a number sentence with numerals and symbols. Tapping. The act of tapping out numbers can help children connect symbols to actual amounts and feel the value. It's especially useful for working with multiples. For instance, ask the children to list multiples of 4. They can begin tapping sets of 4, counting as they go, and every fourth number gets a louder tap. In the end, the children are able to have a list that they can then use to answer multiplication and division problems. Making musical connections. So music is made up of patterns and structures, so it can marry to maths really well. They can also use songs to help them memorise maths rules, or play musical notes for different lengths of time. And putting movement into maths is a really engaging way to help children retain what they've learned. You can play addition hopscotch, or throw a numbered ball when someone has to perform the maths operation their hands touch. Let's have a look now at some of the resources that will really help to build number sense and help the students to build a visual mental model of number. So it might be discrete materials like counters and coins, plastic animals, glass nuggets, cubes, or continuous materials like base 10. They're made up of thousands, hundreds, tens and units. Just to be aware, the 10 flat pieces are represented in 1000 cube. But researchers point out that some learners don't perceive this cube in the way that it's intended, as some learners may think the 1000 cube actually represents 600 because they see 6 faces of 100 ones per face. Numicon is a popular multisensory mathematics teaching program using visual Numicon images in a series of practical teaching activities. There's a really useful supporting handbook for pupils who have particular difficulties with learning mathematics called Breaking Barriers. When Numicon patterns are arranged in order, pupils begin to notice important connections between numbers. For instance, that each number is one more than the last and one fewer than the next. Odd and even numbers and place value. Numicon illustrates number bonds, addition and subtraction, doubling and halving, estimation, division and multiplication. 10 frames are really useful because they present a very clear visual image of how 10 is composed of different groups. Plenty of activities with 10 frames will enable children to automatically think of numbers less than 10 in terms of their relationship to 10 and to build a sound knowledge of the basic addition and subtraction facts for 10, which are an integral part of mental calculation. 10 is, of course, the building block of our base 10 numeration system. 10 frames can provide a first step into understanding two-digit numbers simply by the introduction of a second frame. Placing the second frame to the right of the first frame and later introducing numeral cards will further assist the development of place value understanding. Cuisenaire rods. Ronit Bird, who I reference at the end, has produced some excellent support materials with many ideas on how to use Cuisenaire rods. She says Cuisenaire rods are, in my opinion, the single most useful and powerful resource for helping a learner develop numerical understanding. She's posted lots of videos on YouTube on how to use these, which I've linked at the end. The rods are proportional number sticks, ranging from 1 centimetre to 10 centimetres in increments of 1 centimetre. They are a really flexible tool for developing the understanding that numbers can be portioned in various ways, which support later calculation strategies of decomposition in subtraction and multiplication and division calculations. One of their key advantages is that there are no numeral markings on the rod, so you can assign a value of your choice to any rod, whereas discrete counters become cumbersome as the quantities get bigger. Cuisenaire rods comfortably extend the range of numbers to 100 or beyond. In this example here, in the bottom left of equivalent fractions, because of the rod's different related lengths, children can identify the values of the other rods by using the relationships between them. So here they are marked up. In reality they're not, so we could change the values so that the white is a 5, the red then becomes 10, purple would be 20 and the brown 40. As we see, maths has its own language, whereby there may be multiple meanings for words, full of confusion for a dyscalculic learner, and they can become really overwhelmed by this differing use of vocabulary, which can cause many misconceptions, not to mention anxiety. This is particularly true when tackling word problems. In 2013, the NCETM said, "We know that when solving word problems, it's often not the calculation that children can't do, rather they're not sure which calculation they need to do." So let's have a look at this example. John has £2 more than Dan. John has £10. How many pounds does Dan have? If the dyscalculic learner has learnt more means add, they'll think they need to calculate 10 add 2. This may be particularly true if they've been taught to apply the rucksack method to word problems, when they look for clue words like more. But in this problem, there has to be some level of understanding about what the question actually means. The operation that the learner will need here is to subtract. It helps if the learner can consider what the problem physically looks like, so you can use manipulatives here or draw the story out. So we've got John here and Dan. John with his £10, and we know that Dan must have 2 less than John, so he has £8. The same word problem can be presented using the bar modelling method. The bar modelling strategy is a really excellent technique to help the learner visualise a maths problem. It's a method popularised by the Singapore maths approach. For further information on this method, please follow the links I reference at the end, particularly on the Maths No Problem website. The images can act as a bridge between a word problem and abstract maths that's required to solve the problem. bars of the rectangle represent known numbers and unknown numbers. So the key information we have is we've got the 10 and we've got the 2. And the £10 belongs to John, represented here in the pink bar. And we know that Dan has £2 less than John. So when we represent it like this, the students can see what's missing. And hopefully will understand that if they subtract the 2 from that, it will give them the unknown missing number of 8. Learning the language of maths can be very demanding for learners with maths learning difficulties or dyscalculia. They have to master all sorts of vocabulary and symbols and concepts, and struggling to master these ideas can have a knock-on effect on their progress. So it's useful to have their own vocabulary book or board to hand so that the pupil can refer to this. Take time to break down procedures into step by step with clear, simple terminology. Be aware of the language you use. Explain the concepts carefully. Get the child to develop their understanding by exploring new subject matter and explaining what they think they have been asked to do. Now, sequencing. Consider a child or young person who has problems with sequencing numbers. Start by using the child's own experiences. Ask them to write down the order in which clothes are put on in the morning. This can be a very good way of focusing on the fact that there is a natural order in many things, an order that they will obey but which they've probably never thought about, or the order of events that's undertaken when taking a bath. Include all the details that can be easily forgotten, like putting the plug in or taking off one's clothes. This can be extended into asking the student to describe the journey to school in ever-increasing detail, describing the left and right turns if they walk, or the journey in the car. If the child is particularly challenged over number sequences, you can start with a sequence of just 3 numbers. In each case, in the early stages, have a sequence that comes from real life. So it might be the numbers of the roads passed on the way to school, or the number of their house and the house opposite, or the birthdays of 3 members of the family. When memorising a phone number, like here on the left, what number appears most? The answer here is 7. So start with that. What age were you last year? The answer might be 9. So now we have 7 and 9. And how old is your baby sister? The answer is 2. Tell me your 5 favourite friends at school. And then 5 becomes a remembered number. So it's a way of playing games with number sequences and spatial sequences as a way of training the brain's working memory and getting it to be more active and to take information forward into the long-term memory. Tony Atwood from the Dyscalculia Centre explains that children who undertake just 10 minutes a day of using their short-term memory, using these kinds of methods, he found that they can really expand the capacity of their working memory considerably within a matter of weeks. The key requirement is that it's done for a short, intensive spell every day without interruptions or distractions. So, overcoming maths anxiety. A learner's enjoyment and progress in maths is strongly linked to their confidence and resilience. And many learners feel they'd rather not attempt a question than try and get it wrong, and then that maths exposes them to failure. Fostering the idea that mistakes are good and that's how we learn best is strongly encouraged. Develop a growth mindset. Create an environment where pupils feel safe to explore and discover and take risks and learn through trial and error. They may not be able to understand something, but instead of giving up and feeling they can't do maths, encourage the idea that they don't understand it yet. Collaboration with their peers will help learners to build their confidence in maths and to persevere with a problem, as they don't feel the pressure of working in isolation. So spend time developing number sense at an early age. And use concrete manipulatives in a way that develops understanding. So a maths program that emphasises this visualisation and creativity and spotting patterns and bigger picture thinking plays to their strengths and means that spending time developing number sense as well as using these concrete manipulatives develop understanding. So games provide the opportunity for meaningful practice. It gives the students a chance to interact with their learning and not just follow set procedures. And they're fun, so it removes the stress factor. It increases retention of facts. Research about how students develop fact mastery indicates that drill techniques and timed tests don't have the power that mathematical games and other experiences like that have. Of course, there's the visual input, so you're reinforcing a multisensory approach. And the use of language, so generalising maths vocabulary in an informal way. And as I say, they're fun, and when children are having fun, they're more likely to be successful learners. Ronit Bird has written many books, include lots and lots of brilliant games for dyscalculic youngsters. So how shall we support weak short-term memory? Much of what I'll go through here actually reiterates many of the approaches I've already advocated. So to support visually, using prompt cards or aperture cards, reducing the burden on the working memory. Are you presenting information in more than one mode, visual as well as oral? Present the information in manageable chunks. Do you limit the amount of information given out at one time? So try and chunk information and repeat it. Reduce time, pressure and stress. The slow processing of information requires more time. Discreetly and creatively give them more time. Encourage sub-vocalizing. It's when the student is repeating information quietly to themselves, which helps them hold on to that information. Human interest, so making sense of the abstract. Reference real life experiences to mathematical concepts, like in shopping and cooking. Give them a working buddy where they can work together and explore different approaches to the same problem. Provide a useful facts book or facts card that they can refer to. Lots of opportunities for overlearning. And the CPA principle, so moving from concrete, pictorial to abstract. When learners are faced with a page of calculations, they can struggle to keep track of which calculation they're working on. So aperture cards or reading window cards, or this visual tracking tool, where only one calculation is visible at a time, can really help. Using a 100 square like this one in the bottom right, where the decimal structure builds from the bottom up with 0 to 10 along the first row. It shows how the numbers get bigger as you move up the grid. A learner with left-right confusion will perform calculations in the wrong direction, perhaps, so you can help them by highlighting directions with colours and arrows. I've added an app here called Dyscalculia, which may be helpful, as it reads out a number and presents it as a worded number, as well as illustrating number as bars. Also allow the use of a normal calculator to progress mathematical thinking. And graph paper, it helps with lining up of numbers if there's a problem with visual spatial skills. So in summary, a comprehensive package of support for students with maths learning difficulties should include the following: dot patterns, key facts and derived facts, a CPA approach, lots of games, using small steps and practice, and set the students up for success. Dyscalculia is difficult to identify via one single diagnostic test because of the varied profile. So we're going to go over the diagnostic process after looking at identifying and screening. A teacher can carry out an informal assessment of the learner in the first instance to gain an insight into some of the difficulties that a person may be encountering and to begin the process of identifying a specific learning difficulty in maths. So compare their performance in maths with other subjects and how significant is the contrast. What's their progress in maths like relative to their peers? Do they consistently gain poor test results? And are the problems persisting? If so, this could then flag up potential for a specific learning difficulty. An informal observation in the classroom would involve often the best approach being to ask the student how they're doing the maths and what strategies they're using. Also focus on, can they remember key factors? What's their recall of times tables like? What about their short-term memory and their use of math vocabulary and their speed of response? And look for signs of stress. So teachers have to work on a principle of exclusion. That is, if a pupil is of average or above average cognitive ability and has no problems with literacy or other general subjects, and all other reasons for failure can be excluded, and yet they are unable to understand the maths that their peers are coping with easily, then they might be dyscalculic. To gain a deeper understanding of the young person's needs, screeners are useful. It won't result in a diagnosis, but can provide further information on the needs of that individual. It can flag up a potential problem. So, to lead to a full diagnosis, refer the pupil to be formally assessed through an individual person-to-person diagnostic clinical interview. Deciding on whether to follow the route to a full diagnosis, it can be helpful to consider the reasons behind requiring it. For example, getting a diagnosis may be needed for the student to access extra funding in an education and healthcare plan, or accommodations made in exams, or the disabled student's allowance. Steve Chin has produced this list here, comparing a screener and a diagnostic assessment. So screeners can be used with a large number of students, whereas a full diagnosis is for an individual. Screeners can be used to identify students who might be at risk, whereas a diagnosis is to find the realities and details of a problem and to confirm dyscalculia or maths learning difficulties. Screeners are of relatively low cost compared to a diagnostic procedure, and both screeners and full diagnosis should be intelligible to those involved. Here's a list of screeners that are available that can be used in school. Some are specific for secondary age or post 16, and a few here span across all ages. So diagnostic assessments. We've briefly covered why you would follow the route to diagnosis. It would mean that the student would qualify to apply for an education and healthcare plan, resulting in extra funding for resources in school to accommodate for these needs. It would also lead to accommodations being made in exams for extra time or funding for tools and equipment that might be needed for the student to access the exam. And as they get older, they'll be eligible for disabled student allowance. So, who can diagnose? An educational psychologist. In Waltham Forest, the Educational Psychology Service do offer a Dyscalculia diagnostic assessment, and their contact details are here. Or a specialist dyslexia teacher with AMDA qualification in Dyscalculia. And finally, I'm going to go through a few slides with some recommended resources, some websites and books, all targeted at pupils with dyscalculia and maths learning difficulties, starting with some recommended apps or resources here. So the Dyscalculator is here. A website called Thinking Blocks uses the bar modelling method. Some software programs as well, which are really excellent. This is the list of some really highly recommended websites with some fantastic resources, many of which are free, particularly this Ronit Bird website at the top. As she's such a strong advocate of Cuisenaire rods, she's posted a lot of useful information on how to use them. Can also draw your attention to the mathematics shed link at the bottom here. It's got some really useful information, but also a lesson observation checklist. Some intervention resources supporting students with maths learning difficulty. So Numicon, the Breaking Barriers programme, Numbers Count, The Power of 2 and +1, or Dynamo Maths, all worth investigating. Of course, there will be costs associated. And finally, some further reading. So thank you very much for listening. If you have any questions, then please email me at the address here, and to keep up to date with other resources that we're posting on the Send Success website, follow us on Twitter at Send Success News. Thank you.